Hello everyone, I'm Daniel, most people on the internet just call me Decode, and I'm the creator of AssemblyScript, a language that looks and feels very much like JavaScript with types, but compiles to WebAssembly. I think AssemblyScript is a great option to have to introduce JavaScript developers to WebAssembly and win them over for this exciting new technology, while also making good use of the opportunity to target WebAssembly's feature set specifically in a language designed for it. My presentation today, however, is not about AssemblyScript. Today, I'm here to give my first presentation in context of the WebAssembly CG, that is about WebAssembly, Unicode, and their relationship with the web platform. Or concerns about friction on the web, respectively concerns by non-UTF-8 languages. My presentation will go into a few details of string encodings in popular languages and relevant design principles. And to give a brief overview, it can be divided into the following parts. First, I will present some context on JavaScript's and many other languages' string encoding and related Unicode and language level concepts, including surrogate pairs, UTF-8, binary strings, and what WTF16, which is not exactly Unicode, is all about. Next, I will get to the concern that, on this background, deciding for a single string encoding in WebAssembly's canonical ABI, respectively the interface type's MVP, may introduce complications for the broader WebAssembly ecosystem, and what this means concretely for WTF16 languages, if only UTF-8 is chosen. I will use AssemblyScript as an example here, as I'm familiar with it, but the same or similar concerns apply to many more languages that we want to support well. Afterwards, I will briefly bring up the web's design principle of backwards compatibility, that is especially relevant in the context of WebAssembly as a companion technology to JavaScript. And finally, I would like to kick off the discussion with my suggestions on how the problem may be approached, and would love to have your thoughts on what can be done. So the first detail of the day is what the Unicode standard actually says about JavaScript's and many other languages' string encoding. And as it turns out, it has a very good paragraph already that covers quite some ground on the basics. So allow me to read it to you. Depending on the programming environment, a Unicode string may or may not be required to be in the corresponding Unicode encoding form. For example, strings in Java, C# or ECMAScript are Unicode 16-bit strings, but are not necessarily well-formed UTF-16 sequences. In normal processing, it can be far more efficient to allow such strings to contain code unit sequences that are not well-formed UTF-16, that is, contain isolated surrogates. Because strings are such a fundamental component of every program, checking for isolated surrogates in every operation that modifies, or here also transfers, sends or receives, strings, can create significant overhead, especially because supplementary characters are extremely rare as a percentage of overall text in programs worldwide. For those who are curious, I've linked the specification below, and I will refer to other relevant paragraphs throughout the presentation. Also, the term WTF16 has been used quite a lot in foregoing discussions, and when I initially encountered it, I wondered if this is a joke or something. But I figured that it's actually a thing, as described in the WTF8 encoding, that is a related concept attempting to solve the surrogate problem that I am about to get to. And the document explains WTF16 as well, so I'll again read this one to you. WTF16 is sometimes used as a shorter name for potentially ill-formed UTF-16, especially in the context of systems that were originally designed for UCS2 and later upgraded to UTF-16 but never enforced well-formedness, either by neglect or because of backward compatibility constraints. So whenever I say WTF16, I mean potentially ill-formed UTF-16, as of the previous slide. And it may be useful to evaluate what concrete backward compatibility constraints there were for a bunch of languages to consider the use of WTF16 a good idea, instead of, say, switching to another, more modern encoding. And these constraints were either 1. having to rewrite all code ever written in them that uses affected string APIs if their string encoding and with that their string APIs would change. Or 2, when keeping the APIs intact, to accept a performance regression that can be quite significant depending on use case. As an example, in JavaScript, the affected string APIs are those that accept an index, start, or end parameter, since if the underlying encoding is changed, such an index may not map trivially to the encoding anymore, and hence must be computed on each access, which may become unnecessarily expensive. So sadly, these languages are now stuck with WTF16, and it is likely that they cannot ever change. Another detail I should briefly explain is what these potentially not so well-formed, that is isolated, surrogates actually are. It is not strictly necessary to read the Unicode standards explanation to you, I think, but the TLDR is that in UTF-16 not all values can be represented with just 16 bits, as once anticipated in its precursor UCS2. So a special range within these 16 bits has been reserved, so larger code points can be represented as two 16-bit values, the so-called surrogate pairs. Here's an example of how these are typically represented in UTF-16 languages. As you can see, two surrogate code points are used for our single character. And if well-formed, these always come as a pair, respectively if not well-formed, that is, if there is an isolated surrogate, cannot be conformantly interchanged using Unicode encoding forms. And we are about to see where this may perhaps surprisingly matter. One such encoding is UTF-8. UTF-8, as many already know, is a variable width encoding that represents code points with either 1, 2, 3, or 4 bytes, depending on how large their value is. Due to its design, it does not need to fall back to surrogate pairs, but can instead use more bytes. And as of the Unicode standard, it cannot represent surrogate code points at all, which then leads to a problem if a string is potentially ill-formed. Again, here's an example of how the same string would look when encoded as UTF-8. Note that, contrary to UTF-16, there are no surrogate code points in there, but our character is encoded directly using 4 bytes. And interestingly, there is no mapping for the subsequent example, where I deliberately produced an isolated surrogate, respectively a WTF-16 string. Of course, when using a bit of imagination, it is not hard to see that this may happen in many other ways. On a related note, there's also the concept of so-called binary strings that may be good to mention at this point. In many languages, it is possible to utilize strings as a kind of up to 16-bit values immutable buffer that isn't really a string anymore to represent binary data. And we want to be able to compile code utilizing this concept to WebAssembly as well, of course, since once you put it into a language, people will start relying on it, so it becomes really hard to remove the concept again. As such, this is something we almost certainly will have to deal with anyhow when we want to compile existing code written in many popular languages to WebAssembly. And this also applies to JavaScript as WebAssembly's primary interop language. There, binary strings used to be common prior to array buffer and its typed views like uint8 array being available. And for this and other reasons, there is still a considerable amount of code on the web today that makes use of binary strings. For instance, code may have been written before typed arrays have been available, or a piece of code may target special environments, say intentionally restricted or minimal engines. Sometimes binary strings can also be useful to minimize code, that is, when bundling a string literal is actually shorter than bundling a comma-separated array literal. And of course, there are other non-technical reasons why a binary string may be utilized today. But then, interpreting a binary string as UTF-8 often corrupts the data. And to give a concrete example of where this leads, the link here goes to a frequently asked questions entry over at protobuf.js, a halfway popular library that I authored that deals with packaging up data in binary form so it can be stored or transferred over the network. And of course, if the full 16 bits are used, contained values may map to, you may already have guessed it, an isolated surrogate. For those interested in even more binary string goodness, I've linked the dedicated MDN page covering them in JavaScript below. Which finally leads us to the problem, that is, that double UTF-16 and single UTF-8 are, sadly, incompatible. And once again, the Unicode standard comes to our rescue by informing us that a number of techniques are available for dealing with an isolated surrogate, such as omitting it, converting it into the replacement character to produce well-formed UTF-16, or simply halting the processing of the string with an arrow. So, converting a WTF-16 string, which does not enforce the well-formedness invariant, to UTF-8, which does, will sometimes have to either 1. Trap. That means incompatible sequences are rejected. For instance, passing a string from JavaScript or any other affected language over a WebAssembly boundary may seemingly randomly trap. Some implications are that a. Applications may crash mysteriously, say a long-running Node.js server application, or b. That malicious actors may be able to trigger denial of service intentionally, that is, if they can figure out where and how. Or 2. An implicit conversion must modify the data. That means incompatible sequences are sanitized, using one of the above approaches, and hence the conversion is lossy. In this case, a WTF-16 string passed over a WebAssembly boundary may, for instance, not compare equal anymore. And as you can imagine, there are a couple subtle implications here as well. A. Applications may seemingly randomly not work, store, or read back data properly anymore. Or b. Malicious actors may be able to trigger unexpected or undefined behavior. Unexpected if an operation that previously did something expected suddenly does something else. Or undefined if follow-up code just assumes that the output of the previous operation is always valid. And finally, C leads us to hypothetical security concerns, that is, if authentication tokens, hashes, keys, or the likes are affected. The last point, C, is a bit far-fetched, I admit, but there still is a non-zero probability for what may well become a company's security nightmare. For instance, the Forge library, essentially an implementation of TLS and other cryptographic primitives in JavaScript, still used binary strings a lot not long ago, and still exposes and documents some of these older APIs. Or LZ-string that, as it says, produces stuff that isn't really a string, with the intent to compress strings. And more of an anecdote, there is window.b2a dealing with base 64 encoding, one of the very few web APIs that expect a binary string. And it isn't hard to imagine that similar code exists in many other languages, which is a problem, since we want to compile their existing code to the web, ideally without applying manual workarounds. Note that code migration or similar may not even happen in code you control, but at some point in the future, somewhere further down in your dependencies, so one may not even be aware that the problem is there. Now you may wonder how all of this relates to scoping and layering the module linking and interface types proposals, as presented in a recent CG meeting. As you know, we are about to continue with its next steps, and while I can appreciate the ambitious vision and do not want to block consensus here, I do not necessarily agree with all of the concrete next steps as presented. The first 3 steps are uncontroversial as far as I'm concerned, but number 4 and 5 are relevant in context of what I just presented. In 5, canonical adapter functions are to be added to the interface types proposal, and it is mentioned that this is done to sidestep hard adapter function design questions, like for example how to deal with WTF-16, by fixing a canonical ABI, and the link there then goes to the draft pull request that proposes to settle for UTF-8. So I hope you can see why I am worried, especially since the goal there is to include just the canonical ABI in the interface types MVP, which I think is not minimum viable. Also, I have minor concerns about for, as I would question that this is just an optimization over using a fixed canonical ABI when the single encoding is lossy for many popular languages, or when interfacing with WebAssembly from JavaScript is similarly affected. And as ever so often, there are a few more interesting aspects here, and I collected the most notable ones from foregoing discussions for completeness. One, that having non-UTF-8 languages or hosts on both sides of the boundary would imply unnecessarily re-encoding twice, while potentially trapping or modifying in the process. Imagine, for instance, that there is a larger module graph where this unnecessary work easily adds up. 2, that this especially affects languages running in the browser, since JavaScript utilizes WTF16 for its strings. Note that during foregoing discussions, various potential optimizations in major browsers have been mentioned, but at the end of the day, these are neither universal nor standardized, so we cannot really rely on them. And ultimately, there's the theoretical risk that an UTF-8 based MVP turns out to be good enough for some languages already, so post-MVP work on the hard parts may slow down, in the worst case leaving problems I described unaddressed for an extended period of time. So, as promised, let us take a look at what this means concretely for affected languages. Please note that these issues could affect many similar languages, but I'll use AssemblyScript as an example here, as it is what I have the most experience with. And over at AssemblyScript, which inherits WTF16 from JavaScript, we worry that our language and tools will not be well served by an interface types MVP. Hence, we are very invested in this particular topic. Its options basically are: 1. We could do nothing, that is, wait or hope for adapter functions or any other alternative to land soon. In this case, we would have to accept the overhead from double re-encoding, especially in the browser, as well as indirect effects on code size, say compile the necessary parts of the runtime, just to convert strings. And we would have to document that data corruption may occur when using AssemblyScript in particular, which may confuse our users. It was also suggested that we could try to utilize lists of U16s, but then modules would be unable to talk to VASI and/or browsers directly, that is, without polyfilling everywhere. This one kinda defeats the point of having a string interface type in the first place, I think. 2, it was suggested that we could switch the language to UTF-8, since it is fairly new, and change its string APIs alongside, say by indexing over bytes instead of over char codes as commonly known in JavaScript. Sadly, even though it is rather new, this would not only be a significant undertaking, but ultimately also lead to breaking with all existing AssemblyScript code using these APIs, which is very similar to why other languages did not make the switch. And of course, we would have to sacrifice a little more of our goal of being close to JavaScript, be it to provide a familiar solution for JavaScript developers, or to have the option of writing portable code that compiles to both WebAssembly with ASC and JavaScript with GSC. Another suggestion that has been made was that we could provide a separate UTF-8 string class. But then, doing so would hurt developer experience, and that it would of course be better if one didn't have to worry about working around the problem by hand. And it is also a slippery slope, in that users may have to convert strings hence and forth frequently, or in an attempt to avoid this, we may end up with 2 separate standard library variants, or even 2 separate ecosystems of modules for 2 different string classes. Lastly, we could work around the problem in a similar way as Swift does, using a clever mechanism to cache some of the otherwise expensive computation effort that was already done. But again, this is a significant undertaking that still makes string API slower than necessary, while increasing the code size of emitted modules, so we are not exactly keen of it, also since adapter functions would be the better alternative. As a side note, this option is similar in nature to the idea that I originally coined universal strings, and mentioned in some of the discussions, but others told me that this name is a little silly, so I decided to shorten it a bit to imply less. I will get back to this one in a bit. As such, at AssemblyScript we would prefer support for WTF16 in an interface types MVP, so we can lift and lower strings to and from other AssemblyScript modules, to JavaScript, and other languages, also since we do not know what JavaScript and browsers may do in the future. So it's hard to make any informed decision right now that would justify taking the risk, respectively investing the effort. And since we are here, I figured it may also be good to mention one of the web's design principles: backwards compatibility. This is from a design guide published by the World Wide Web Consortium, titled "What is a Good Standard?" An essay on W3C's design principles. And it identifies two kinds of backwards compatibility. One, that a new version of a specification must be backwards compatible with a previous version of the same specification. And two, that new technologies should be backwards compatible with earlier technologies. It then continues with the following paragraph that explains it better than I could. So allow me to read this one to you as well. Nobody forgets about the former, because there's nothing the developers of a new version know so well as the previous version they are trying to replace. Backwards compatibility is always hotly discussed. But the latter is less obvious. It is, in a sense, the complement of extensibility and modularity. Whereas those two stress the importance of developing technology in such a way that it will work together with future new technologies, backwards compatibility stresses the importance of working well with what is already there. No new technology is designed in a void. And of course, I'm thinking about WebAssembly as JavaScript's new companion here, with both of them being part of the web platform. To recap, what are the takeaways here? UTF-8 is certainly the more modern encoding, and anything designed in a void should perhaps use it. Yet WTF-16 is the reality we live in and have to deal with one way or another. Many WTF-16 languages are stuck with their encoding and will likely never change. You know, it's, well, complicated, but we still want to support them well. Interface types, however, desires only UTF-8 in its MVP, but then, unfortunately, is lossy for WTF-16 languages, including when interfacing with JavaScript. Also, on the web, backwards compatibility is important, respectively is a design principle. And sadly, part of the WebAssembly ecosystem will likely suffer, since legitimizing a canonical ABI with just one encoding will inevitably produce winners and losers. So I thought, what would be necessary to produce winners here? One, and this one seems like the most straightforward one to me, we could specify both a canonical double or UTF-8 and a well-supported legacy WTF-16 string encoding right away, with two sets of lifting and lowering instructions. Here, we would make clear that the more modern encoding is the recommended choice for new languages perhaps, but we would also give a clear signal that WTF-16 languages and backwards compatibility on the web is important to us. 2. We may start with only WTF-16 as the canonical ABI string encoding. That means to start from a position of at least having lossless encoding where WTF-16 languages, including JavaScript, are involved. And by doing so, invert the, as we say in Germany, Bringschuld, that is, that the burden of proof is now on others, say that we require really good arguments why not tackling the edge cases respectively breaking with the principle of backwards compatibility is actually okay. Even then, we can still iterate from there towards support for UTF-8 in addition, ultimately leading to one again, which I would welcome. 3. We could not split out adapter functions from an interface type's MVP. So choosing a single canonical encoding would become unnecessary in the first place. This one would leave the details open for now. 4. We may investigate WTF-8 as the canonical ABI string encoding in another attempt to at least tackle the surrogate problem. But then I wonder whether WTF-8 would fit actual languages, or if these would still have to perform a check at the boundary, whether we can actually reasonably convince ourselves that re-encoding twice, especially in the browser, is okay, and what the implications of potentially ill-formed WTF-8, which is interestingly again a thing, that is, with surrogate pairs encoded as individual surrogates, would be. 5. It was suggested that we could specify 2 string types and convert implicitly where necessary, but I do not quite see how this would be considerably better than the alternatives, especially in a future with GC. Let me know though if you see a way to make it work. 6. And here I get back to my idea of a unistring again. We could specify a first-class string primitive that abstracts Unicode-like encoding differences away. That is, caches re-encoding work already done, say using multiple slots and a bit remembering well-formedness as outlined in the accompanying document, or alternatively, using a breadcrumbs mechanism, while already working towards a solution that would integrate with GC as well, since in GC we'll eventually be facing the same problem. If you're interested in this idea, I can offer to present it in a future meeting, of course. And 7, there are likely more approaches to solve the problem, so if you have ideas, novel or not, please let me and others know. Also, I would be particularly interested in the thoughts of other language implementers, especially those working on other affected languages. Lastly, I would like to invite everyone to discuss how we, as a community, can enable a flourishing, polyglot WebAssembly ecosystem where everyone, including the web platform as a whole, is a winner. Last but not least, thank you for bearing with me for so long. I hope this was helpful to provide the necessary context. Please share your feedback and of course feel free to hit me up on other channels at a later time if you'd like to discuss these aspects more closely. Thanks.